Hello. Before we start today, we have a little promotion from the Linguistic Student Union for recruiting some new executives. So, if one or two of them would like to talk about it and unmute, that would be fantastic if they're here and ready.
Hi. Sorry about my internet is a little bit spotty, so it might not be the best, but so hi, I'm Corey. I'm from the LSU, which is the Linguistic Student Union. You might know us from we are the one that made the Discord server for the linguistic students. You might have seen our merch floating around from last semester. So I'm here to talk to you about we're looking for new execs for our team. Um, we're holding a by-election, which will be on the 31st, because over the past 2 semesters, we've had some of our executives graduate. So we've have some new spots that are opening up. I think the LSU is it's a really great place for you to just like meet people in linguistics, also build some experience. This stuff looks really good on applications. So yeah, so we have quite a few. We have quite a few positions open. Let me just pop up my script here. Yeah. So in the chat, um, Yolanda has put in the link to our application form, where you can find all the available positions open, as well as the description for the positions as well. So the deadline to apply for that will be on May 28th, and then our by-election will be on the 31st. Does anyone have any questions regarding this? No? Okay, well, thank you very much.
Yeah, it looks like there are secretary, treasurer, events coordinator, communications director, department representative, merchandise officer, fast representative, and council representative. Um, I believe the department representative gets to attend department meetings. So if you're an undergrad student who likes to kind of see behind the meetings and see how disorganized your professors are and what's going on behind the scenes, it's a great job. That's just a little sort of fun thing if you like to get involved. Um, it's a little special privileged position. A grad student gets to do it too. It's always a fun job. And of course, events coordinator is fun too. The LSU has been revived several times during my stay at SFU. When I first started, the LSU did not exist and it was revived. And by the time I graduated, it died again. And it has been picked up since, I think, in 2015 or 2016. And it's been alive ever since. So please keep it going. Um, yeah, deadline is 28th. The by election is 31st. So only 3 days, but usually with these student union positions too, it seems like a lot more work than it actually is in the end. So don't be too intimidating by it. I'm not saying it's not work. I'm just saying it looks good. It's good to get involved. And in the end, it's not gonna kill you. Okay. So today we're gonna talk about set theory in the end. Your assignments have been submitted. So when those are graded, those will be released, and once the grades have been released, a full solution video will be posted on Canvas. So as soon as you see the little email that says your grades have been released, on the front page of Canvas, there will be the solution video, so you can look at that, and I will go through every question in detail. Um, and there will also be a YouTube link in the lecture video page as well if you don't want to look at it on stream.sfu.ca, which will be on the front page. Um, The grading will be there too. During this lecture, I'm just going to go over two questions that so far I've seen some difficulties with and that I received a couple emails about. So those will be released sometime today when I get them all marked. Furthermore, what I want to say first before those grades are released, the grading scheme for this course is the grading scheme I've used in the past when I marked assignments and tests differently, when the course was focused on tests and not on assignments. So when I did assignments based on completion and not on correctness. So uh, if the grades don't seem as high as they should be, don't worry about the overall grades for the course. Don't look at the scale and freak out. I added a little clause to the grading scheme that says, at least a quarter of the class will get an A minus or above, at least 5% will get an A plus. Things will be scaled in the end. So don't worry too much about the scores if they're, if you look and say, oh, 75%, that's like a what is that, like a C plus in this course or something. It looks harsh, but it'll all be boosted up in the end, and the tests are not probably as hard as the assignments, so it'll all balance out in the end. Okay, so the two questions I'll talk about are one, the good and not great, and then we'll talk about the presupposition question about John eats only pizza because that one seemed to be difficult so far. Okay, so good and not great. I'm going to give you a different sentence to evoke an emotional response from you because I feel like when we talk about other people, you might not get the same inference as when I talk directly about you. So here's something you probably heard before from a professor. Yeah, I think you wrote a good paper. Okay, I'm going to ask you a genuine question. If I told you this, I think you wrote a good paper. What grade do you think you would have got on that paper? Do you think that's an A plus paper? If I just said, I think you wrote a good paper.
I'd say B or B plus.
Okay, so you might ask me then, what would I have to do to get a great paper? What would I have to do to make it great? So there's an inference here, which is I think you wrote a not great paper. So it's the same sort of inference with Tails. Tails is good at carrying Sonic, which implies that Tails is not great at carrying Sonic. So there's a scale with these words where if I say it's good, there's an implication that it's not great. There's an implication which is it's not fantastic, it's not perfect. Um, if I say it's like, it's decent, usually that means like, oh, it's not very good. So if I say something that's lower on the scale, I imply that it's not something higher on the scale. So that's sort of what's going with this. Um, but you can always reinforce it because I can say, uh, yeah, I think you wrote a good paper. In fact, I think it was great. I think it was fantastic because maybe the language that I use was not um, overly strong to begin with because maybe I'm just not someone who uses very strong terminology. Maybe that's just my personality. So it can be reinforced, like in the beginning when I say, I think you wrote a good paper. In fact, it wasn't great. Or I can cancel it and I can say, yeah, I think you wrote a good paper. In fact, I think it was great. So, um, maybe when it is about you in an academic setting, it's a little bit more clear what the implicature is here compared to when it's about someone else just doing some other activity, which is good and not great. So I don't know, does this example resonate a little bit more with people of why there's an implicature here and not maybe an entailment or nothing at all? Because I think the most common response I got for this one so far that I've seen is that it's either nothing or there's entailment because it's contradictory. Um, which if you get contradictory, maybe because good and great are the same thing to people, but typically it's on a scale where great is better than good. So out of all the four, this was the most problematic I've seen so far. The rest of them were pretty well done in general, so I'll leave those to the solution video. And of course, when you watch the solution video, I mean, don't hesitate to ask for more clarification if you need it later. And then for two, okay, two, Papa John eats only pizza. Papa John doesn't eat anything else, or Papa John eats pizza. Okay, so I'd say about 70% of the ones I've seen so far got it right. One of these was entailment. So A is entailment, not presupposition. If we say he eats only pizza, then logically, Papa John doesn't eat anything else. But if we do an attitude test here and we ask a question and we say, does Papa John eat only pizza? We still make this assumption that Papa John here eats pizza. We don't make an assumption that he doesn't eat anything else because we're questioning if he only eats pizza. He could eat other things. We're not assuming that he doesn't eat anything else. We're questioning that fact. If we make it a negation, Papa John does not eat only pizza. We're still presuming that Papa John eats pizza. In fact, we're denying A here. We're saying that he eats other things. So we can't be presupposing A because when we negate Papa John eats only pizza, we're actually denying A in this case. So A cannot be a presupposition here. When we negate it, we're losing that entailment. So there's more evidence there that that's in fact an entailment because when we negate it, we lose it. You can do a conditional here too and get the same idea. If you rely just on the accommodation or failure test, it might not have been very clear which one it was. So, the attitude test preserves presuppositions and kills entailments and implicatures. So the attitude test is really the strongest test you can use for presuppositions. I mean, it's going to preserve them. It's going to make them, I'm not going to say still obvious because it might not be obvious to begin with. But you're going to find them in the negation. You're going to find them in the question. So you'll find them in all three versions compared to, the accommodation or failure test where you might find presuppositions in places where they don't exist. Just in case maybe you've misinterpreted it or maybe it just happens to coincidentally work out in some cases. So those were the two questions that I think the ones I've seen so far people have struggled with the most. So with just those two, were there any questions about the ones I've just went over? I mean, or any questions about the other ones that you want to cover really quick?
I have a question about implicatures.
Yes.
So when you do a cancellation test and you're denying expectation,
Mm-hmm.
It still needs to make sense, right?
Yeah. Yeah, it should still make sense.
Okay, thank you.
I guess I should add one thing to this is that you may need to make a context for it to make sense. So it might not make sense in every situation. You may have to construct a specific context, like with the specific number example we did with John. It does sound a little weird for it to just come out of nowhere. So you may have to make a situation for it to really work. But it does have to make sense in some specific context. Okay, if that's it, we can always wait until the solution video for everything, just to save some time. And then if you have further questions, we can talk about it on the discussion board or over email. So going back to set theory, here's where we finished last time by talking about the set conventions. And before we do the exercise, I want to talk linguistically about what we did. So basically, we talked about objects in sets. Now, what linguistic element are we really talking about when we talk about these objects and elements? And what we usually refer to are proper names. All of these different things are usually proper names. They're collections of people or things. So when we talk about, where do I have room here? Let's just get rid of this stuff. When we talk about sets of things, so usually, well, proper names, or like you can think of even sounds as like a type of, well, I don't want to say a type of proper name, but if we think about, say, the vowels or consonants, these are things we've already done. But in syntax, when we think about, say, the group of possible subjects for a sentence, or when we think of a pronoun in a sentence, and we ask ourselves, okay, you have this sentence, he went out, and you're looking at a group of people in a room, and you ask yourself, okay, you have this word he, who could he mean? And there's this set of people that he could refer to. So usually the objects that he could refer to are, the elements in a set. So like this A, B, C, D, instead of using these abstract letters, we would pick proper names, and these are the people that he could refer to, or she, or they. In the case of they, which could be singular, you'd have objects. In the case of they, which could be groups of people, like plural, you might have groups of people. So, like we see here, where you have a set containing two people. So maybe if they is plural, you might have two people, Jim and Carol, and they could refer to both of those people at the same time if they was plural. So, uh, yeah, that's usually what these objects refer to in terms of syntax. Um, or, if we talk about, say, Ling 324, we could have a set that describes every single person enrolled in Ling 324. So we could fill our setup and just go through the list of everyone in the Zoom chat. Uh, and we could go down the list, and I'd have to fill out 21 names in the Zoom chat plus an extra 19 on Canvas, and that would take a while. But these are what our objects are in linguistics. So abstractly, we learn the concepts, and then when we apply it, we usually use proper names. So this first exercise is just a few true or falses to see if we remember how to use the element symbols. So why don't we take, well, let's just do one quick one, so that way to refresh our minds, and I'll give you like 3 minutes so you can try it on your own. So we have a set A, which contains a bunch of different elements. Usually what I do when I first start these exercises is I would draw it out and I'd place all my elements inside. So it's the first one. So sure, I'll write it out. I have Y, Z, Q, X. I have a set containing RT. So what I would do is I would leave these in a set together, and I would not separate these because it's just one element. I have V, I have a set containing W, and I have Y again. So I have Y twice. And one of the conventions that we use is that if we see the same element twice, is we just ignore it because we don't count the same element twice. So, okay, this is our set A, and now we just go through each one and we ask, okay, is that thing an element of our set? So is X an element of our set A? So we take a look and we say, okay, is this thing just X on its own in our set? And yeah, I find it right there. X on its own, that's in A. Or I can just take a look at the notation above and I find X on its own right there. Okay, so X is in our set. So we can say, yeah, that's true. X is in our set A. And then we can go with the rest. So why don't I give you 3 minutes to try this on your own, and whatever you can get done, great. And we'll talk about the answers then. So if you have any questions, as always, you can speak up over voice or talk in chat and I'll help you out. But otherwise, I'll see you in 3 minutes. Okay. See how we feel about these. So for B, do we think B is true or false? Does the set X
False.
contain an A? We see some falses here. False, false. That is correct in this case. And that is because we do not see the set X contained in A, we just see X itself in A. So that would be correct. If we wanted to see the set X in A, we would need to see that whole thing as a unit. So yeah, it's good to treat this just as like an image or a symbol. Do we see R as an element of A? So for C, is that true or false?
False.
It is also false. That is good. This is good. So this is typically a misunderstanding. A lot of people at first tend to say true for this, but this is false. So in order for this to be an element of A, we just need to see that on its own. So we would have to see R on its own. Um, so even though we do see R in this set here, it is in a unit, so we cannot break this apart. So R just has to be on its own in order to be an element of A. Now, what about D? Is the set containing W an element of A? Okay, before I answer C, Bradley asked, would it also be false if it was the set containing R? Yes, it would also be false if it was the set containing R. So if we had the set containing R as an element of A, This would also be false because we would need to see just this on its own. But in this case, we do not see just that on its own. So yeah, so for D, when we have the set W contained in A, we do see that right here, set containing W. We also see it in the set above, in the formal definition, curly braces. So yeah, D is true. Okay, so A, B, C, and D use that set A as an image, and then E, F, and G use their own separate sets. So E, again, we're looking at symbols here. So this was the set containing the set containing C, and we asked if this was an element of the set containing the set containing the set containing C. That's a mouthful. So for this one, do we think this was true or false? I see 3 trues already. Yeah, so there's a couple ways of doing this. You can either draw it out, or you can just take a look at the brackets. So we have 2 brackets around the first C, so we can see if we can find that same thing. Okay, so this is the element here, and it's contained within another set. But if we were to draw this, we would have, yeah, I'll do this one in red so that way we know this is the first one. This would be like this set here. And then we find this element here if we draw it out. So basically the first set of brackets is our set, and then everything else in the brackets are the elements. So this would be a visual representation of E. What about F? Is the empty set an element of the empty set? Oh, finally some ideas that are conflicting in the chat room. Okay, we'll do this one in green. Okay, so I'm going to draw the empty set. Okay, so that's the empty set. And I'm asking if the empty set is an element of that set. So if the empty set is an element of that set, what that means is I have to find this thing inside that set. But I do not find that inside this set. Therefore, this one is false. So we got rid of both lines. So basically what this is asking, remember, we can write this a little bit differently. So we could always write this as saying like, this is the brackets with nothing inside. So when you have an empty set, nothing is an element of an empty set. So if we ask ourselves, is the empty set an element of the empty set? The answer will be no, because nothing is ever an element of the empty set, not even the empty set itself. So the empty set is not an element of the empty set in this case. Finally, for G, is F an element of the set containing F? We'll do this one in blue. So here's the set. The element contained is the set containing F. And here are some very quick falses. Yes, this is also false. So F is not an element of that set. Only the set containing F is an element of that set. So A, B, C, and D are really just testing, like the basic bits, and then E, F, and G go a little bit further into the symbols. So when you get more complex set notation and you look at sets containing sets, empty sets, and elements containing, or elements in sets containing sets, it's a little bit more notation heavy. But again, don't let the notation boggle you down. It's still the same concepts. You can just treat them as little symbols or characters. I know this is a far-fetched at the beginning, but if you consider math notation the same as the IPA is a little bit intimidating at first, but eventually you get used to it. Math is the same way. It's just concepts hidden behind notation. So it looks a little bit scarier, but it's the same idea. So before we move on, are there any questions about these 7?
If you had a set containing the empty set, then would empty set be an element of that set?
Yeah, so I'll show you what that looks like. So we would have, okay, so this statement is true. The empty set is an element of the set containing the empty set. So this statement is true, and visually, this would look like that. And basically, that is because you can find the symbol within that set. Can I explain G again, please? Yes. Okay. So F. Okay, so this is the set. Okay, here's the set. The set is the set containing the set containing F. So this is basically the set I'm looking at. The set is the set containing F. Now, if I want to find F, I'm asking, is F an element of that set? So if this is true, I need to find just F on its own in that set, because I'm asking, is just F an element of that set? The answer to this is no, it's not just F. What I have as an element is the set containing F. So F and the set containing F are two different elements. Again, we want to think like computers and not like humans. So humans might think, okay, these are the same thing, the set containing F and F, because we can just open it up and dig into it. We see F right there in our heads, but computers say, okay, now this is a separate thing from F itself. One is a set, one is an object. So F itself is not in that set. So to make G true, we would have to say that either F is an element of the set containing F. So that would be okay. Or we would have to make it so that the set containing F is an element of the set containing F. So both of these would be true. So those are two ways to repair that. But this first one does not work. Is there a question? Anna, your mic is on. Is there a question? Okay. Okay. Okay, so let's continue. So here's the next bit, and I think you'll all be pretty quick with this. We kind of talked about this. So the size of a set. The size of a set has a special word. You can call it the size, or we can call it the cardinality, not to be confused with anything religious. And this is written with these absolute value bars. So if you ever see something like vowels with 2 bars around it, this just is asking how many things are in that set of vowels. So for instance, if we talk about the letters themselves, we would say that the cardinality of the set vowels or the size of vowels is 5. So how many elements are in the set? So a set can be finite, it can have a certain number, or it can be infinite and go on forever. So here's some questions. Determine the size of the following sets. And we'll just do these together because these are pretty straightforward. You just count. How many elements are in P? Okay. 1, 2, 3, 4, 5, 6, 7, 8, 9. Okay. The size of P is 9. Okay. I'm going to ask you about E and F. I will ask you about E and F. So when you can figure out E, how many elements are in E, the empty set? Type that one when you figure it out. E is 0. Okay. So E is 0, F is 1. F is 1. Okay, so E is 0 and F is 1. So let's talk about this one. And I'm just going to draw these. So the empty set, remember, can be represented as like a set with nothing in it. So visually, this is like a circle with nothing. There's nothing inside this set. So it's 0. It has no elements. But the set containing the empty set can be written like this. And this is not a pretty notation, so this is why I don't do this. But it can be drawn like this. So we can see a contrast with how many things are inside this set. 0 things versus 1 thing. So E has 0 things inside that circle, F has 1 thing inside that circle. So a contrast there between the set E and the set F. So another thing is like you take a look at those curly braces and you count how many things are inside. What about D? So this is a fancy letter for all the integers out there. How many things are in the integers from negative infinity to positive infinity? Oh, I guess that kind of gives away the answer to that. Okay. Infinity, that's not green, whatever, that's okay. Okay, E and F. So the sets X and Y. Here's a good contrasting question, another conceptual thing to help you distinguish between objects and sets as elements. So X, yeah, three elements for X. And then Y, which is F. I should have chosen letters that were consistent. I'm just learning this now when I ask. Y has 4 things. So yeah, so if we just count, the set X has F, A, and then it has this unit BC. So there's 3 things. There's F, there's A, and there's the unit BC. So BC is treated as 1 unit. While in Y, or question F, you have F, A, B, and C. So in that case, B and C are treated separately. They're not a single unit. So that's why there's a contrast between 3 things in part E and 4 things in part F. Okay, are there any questions about size here? Believe it or not, the EF contrast is actually important. So it's not brought up just because like, oh hey, let's just demonstrate this. It's useful for something we're about to see with set operations. Okay, good. Recursive set generation. There's a slide here about how we can generate sets in an interesting way. I'm not going to cover this in a set notation, but I do want to talk about it in terms of syntax. So you can ignore what's being said in the slides here. I just want to talk about it in terms of syntax, and we can kind of see how it can be done in sets. So in syntax, we have recursion, which is this property where we can repeat the same rule over and over and over again to generate these infinitely long sentences. So we can do this with just noun phrases, with 3 rules, or really 2 rules. We can take a noun phrase or a determiner phrase, however you want to do it. And we can say it goes to a determiner, a noun, and then an optional prepositional phrase. So we put it in a bracket to mean it's optional. And we can have a prepositional phrase that goes to a preposition and then a noun phrase. So we can write it in this notation, or we can do it in like a tree. So it goes to a determiner, a noun, and a prepositional phrase. And then the prepositional phrase goes to a P and an NP. So we can take these bases, and then what we can do is we can just repeatedly apply these over and over and over again, and we can essentially create a noun phrase that is infinitely long. Because every single time we see this prepositional phrase, we can just apply it to itself. And every single time we see the noun phrase, we can apply that rule again to itself. So we can see the NP will lead to a PP, which leads to an NP, which leads to a PP, which leads to an NP and a PP and an NP and a PP. And it just goes on forever and ever and ever. So this is recursion. Of course, eventually you need to end the sentence. So that's why the prepositional phrase is optional. So eventually you can say, okay, I don't want a prepositional phrase anymore, and you can terminate it. But with sets, you can have sort of the same idea. So really what we do with sentence structures to create an infinitely long sentence is we're not doing anything intense. Really all we're doing is taking two rules generates an infinitely long NP. 2 rules. So we're taking really, really simple concepts, something really, really weak, and just applying it over and over again to create something really powerful. And we can do the same thing with sets. So again, I'm not going to go through this example in detail, but we can start with something and we can say, okay, I want the number 1. And I can say, if I have some number in my set, what I want to do is I want to add the next number to that set. And I just want to keep doing this over and over and over again. Okay. So after I repeat that an infinite amount of times, what I end up having is the set containing all the numbers from 1 to infinity. So the way that we generate these infinitely long noun phrases is the same way that you can generate sets that are infinitely large. So I sort of introduced that backwards in the sense that here's this linguistic thing and here's how you can do it with sets too, when really in reality it's here's this interesting thing you can do with sets. Now here's how we can apply it to linguistics. But that's something that we can do with set theory, and that's how we apply it to linguistics. It's the same sort of concept. We can take 2 really simple rules or a few really simple rules and get something really powerful out of it, just by repeatedly applying the same things over and over again. And that idea comes from set theory. It comes from logic. It comes from mathematics. And linguists take advantage of it in syntax. So that's just a side thing that comes from math that we apply in linguistics in general. So nothing you really need to know from that, just a little side exploration. Okay. What we do need to know, though, is a nice way to abbreviate sets, because in this course, when we talk about nouns and we talk about verbs and we talk about prepositions and adjectives, the sets get really big. And we often need to talk about things and sets where we don't know all of the elements inside. And what we've been doing so far is we've been listing all of the elements inside the sets. And we've been using really short sets for that reason, because when we talk about vowels, it's nice. It's A, E, I, O, U. But as you can see here, With the consonants, if we want to talk about the consonants every time, we got to write a lot of consonants out. It's 21 with letters. If we do the IPA, it's even more. And that would be awful. So what's nice is that in set notation, there's two different types. We've been doing something called list notation, or it's also called enumeration. Basically, you just list out every single element, which is fine. But what we often do once we're no longer, learning the basics and trying to pick out individual elements, is we use something called predicate notation. And this is when you describe sets with a description. So instead of picking individual elements, you just describe the set, and then we understand the set based on a description. So there's a nice little form here, and now we use variables. So you have a variable that you specify. Usually this is a letter like X or Y or Z. We use a little bar. Sometimes you use a colon. And this is read as such that. So this is like your formal mathematics term. So we'd say we have this set of X such that X is some description. So I think it's best to use an example here that we have. So for instance, here we have C. This is our set of consonants, B, C, D, F, G, H, J, K, L, all the way up to Z. I can list all these elements out, or I can abbreviate this. And I can say C, this is our set of consonants, X, such that X is a consonant in English. So these sets are the same set. They're exactly the same. They have the same elements. The only difference is the first set is written out with all of the elements in list notation, and the second one is written out with a description. And the second one is advantageous for two reasons. First of all, it saves us a lot of time writing. And the second thing, which is really nice, is that we don't actually have to know what's inside the set to work with it. And you might think, hold on, why would we ever need to do that? Well, what if we wanted to talk about, say, everyone enrolled in Ling 309, and we wanted to compare it with the people enrolled in Ling 324? Well, I don't know who's enrolled in Ling 309, but if we want to make comparisons and to see who's similar, or who, like all the people in both, or who's in 324 but not in 309, or who's in 309 but not 324, we can still discuss it. We might not know specifically who's in it, but we can still talk about it. And that's what we want to be able to do. So with predicate notation, we can at least still set it up. In list notation, it'd be difficult to do that because we'd have to be able to write everything out. So predicate notation has its advantages. Or on a large scale, if we think about talking about the population of Vancouver, that's something that changes consistently. Who lives in Vancouver right now? In list notation, you would be updating that thing every single minute. In predicate notation, we don't have to worry about updating that list. It's just a description that stays the same, and you have some computer system in the background that updates it whenever you need to run it. But you can always keep that discussion going, and you don't have to write a list of 2 million names on the screen. You can just have a description. So another example, of course, I don't know. Again, Link 324. We want to talk about the students in Link 324. How would we write that? Link 324, talk about students, X, such that X is a student in Link 324. That would be the same thing as writing all of your names. So instead of writing 40 names out, just write the set of X such that X is a student in Link 324. You could do any course with this, or you could even do SFU. X such that X is a student at SFU. There you go. I have just saved the time of writing the names of like 60,000 students just by writing it in predicate notation. So this is another way of writing out sets that is much more convenient that we'll be using a lot more often after this lecture. So are there any questions about set notation or anything we've done so far today? Okay, let's take a 10-minute break and then we'll come back and continue. So if you have any questions, you can leave them in chat or I'll come back and answer them after the break. But I will see you in 10 minutes. Okay, how were those construction noises? Did you feel like you're back at university? It's lovely, wasn't it? Very nostalgic. Yeah, yeah. What's amazing is that there's still construction up there, but there always will be. Okay. Um, yeah. Next topic. Subsets. Subsets. Okay. Subsets often get confused with elements, and this is where things can go a bit awry. So remember, elements are about whether an object is in a set or not. Subsets are basically asking about, or not asking, subsets are about parts of sets. So having a set inside a set. So formally, we could say a set A is a subset of B if every set in A, or sorry, if every element in A is also in B. And we use a different symbol for this. We use this symbol here. A is a subset of B. And it looks a little bit similar to the less than or equal sign. So I have an example for you, and I want to illustrate this example. So here we have the numbers 1, 2, and 3. And we have our big set here, B. Okay. Now the first set I want to take a look at is the set A, which contains 1 and 2. Okay, so notice the circles here. Now what my claim here is that A is a subset of B because the set A is contained within the set B. So I'll write this out specifically, and I'll say the set containing 1, 2 is a subset of the set containing 1, 2, and 3. And I say this specifically because each of the elements in A, so 1 and 2, are also in the set B. So visually, this works out because we can circle all the elements in A, and we can circle all the elements in B, and everything in A is also in B. But also, if we just take a look at the sets in the set notation, we can take a look at each element here, and we can find it in both of our sets. So we can take a look at everything in A, and we can find it directly in B. So because both of those things happen, we know that A is a subset of B. Okay, so this is different than element. If it were an element, we'd be looking for that specific thing 1, 2 in that other set B. But in this case, we're just looking to find like a part of B. We're basically saying that the set A is like this set inside B. It's a part of B. Okay, so that's one example. I'm going to basically copy and paste the same thing. And I'm going to make this a small boy over here on the side. And I'm going to use a different example here. Okay. So now I'm going to do A and C. And we're going to contrast these two. So here's my set A. And now my set C is going to contain 1 and 3. So I will do this one in blue. So here's my set C, and these are just in the example above. So A is 1 and 2, and C is 1 and 3. Now, if we take a look at A and C, these sets are not contained within each other. Like A is not contained within C, and C is not contained within A. Like they each have an element that's outside of each other. So if I ask myself, is A a subset of C? Specifically, I'm asking, is the set containing 1, 2 a subset of the set containing 1, 3? I look and I say, is 2 in C? Well, no, 2 is not in C. 2 is just in A, it's not in C. So if I take a look here and I ask myself, where is this in C? It's not in C. So the answer is no. A is not a subset of C because I cannot find every element in A also in C. If A were a subset of C, I would be able to find every element of A in C. So if you compare this image with the original, where A is a subset of B, you can clearly see that entire set A is within B, while on the image on the right, A is outside of C in this case. I meant to keep that note there. If we ask the same thing for C, like we can reverse this and we can say, is C a subset of A? And the answer would be the same thing in this case. The answer is no, because in the reverse direction, we ask ourselves, well, is 3 in A? No, 3 is not in A. 3 is only in C. So even in the reverse direction, you know, we cannot find 3 in A. We find 3 only in C. Sure, 1 is shared between the two, but we don't just need 1. We need every single element in one set to be in the other. So this is how subsets work. Basically, if A is a subset of B, and this is just general sets A and B, then everything in A has to be contained within B. This means that you can draw a circle around A, you can draw a circle around everything in B, and all of A will be inside of B. This also means that A and B could be the same. So you could have something like this, where you have A and B, and they're exactly the same. That would also be okay. And this is why I draw a comparison to the less than or equal to sign, because it's okay to have something like 3 is less than or equal to 3. So it's also okay to have something like A is a subset of A. That's perfectly fine. So I make the comparison because the comparison works the same thing or it works the same way for subsets. So are there any questions about this example before I talk about a different type of subset, a proper subset? Okay. If you do get questions, interrupt me with these ones. Okay. So proper subsets are not used that much at the Ling 324 level, but in graduate semantics and higher levels, they are used. So we introduce them here just so you're aware of them. Proper subsets use this symbol. So the difference is that there's not that little equality at the bottom. So this is a lot like the less than sign, and the restrictions are the same. A proper subset is a subset, but they cannot be equal. So A, if we have some set A, it has to be smaller than B. So that's like the only restriction. So if we have something like, say, 1 and 2, and I won't go in as much detail here, I'll just draw these. Let's say this is E, and let's say this is F. So E and F both contain 1 and 2. Although E may be a subset of F, because everything in E is contained in F, E is not a proper subset of F because they're the same size. So basically, a proper subset is just a subset, but they're not equal. So what would be a proper subset? Well, again, I'll just draw the same picture over here. So this time, let's say this is D. And let's use F again. So that's F. So in this case, we can say D is a proper subset of F because D just contains 1, F contains 1 and 2. So everything in D is an F because we can circle all of the things in D that's contained in all of the things in F. Therefore, D is a proper subset of F. D is also a subset of F. So if D is a proper subset of F, then D will be a subset of F too. Again, the only difference between a proper subset and an actual subset is that proper subsets are not equal. That's the only difference. And in terms of like natural language, this would be equivalent to a phrase like some but not all. Like this is where you would see it in terms of quantifiers, like some but not all dogs like bacon. So a subset can also be a proper subset. Yeah, a subset can be a proper subset as long as the subset isn't the same size. Or sorry, isn't the same size, so they're not equal. So like this is the case where a subset is also a proper subset because one is smaller than the other. And then this is the one case where one is a subset but not a proper subset, and that's because they're equal. So one way of thinking about this is like all I'll type this out. You don't really need to know this, but I'll type this out. All proper subsets are subsets, but not all subsets are proper subsets. And the best way to think about this again is just like the less than sign or the less than or equals to sign. That's just how they work. It's probably the quickest way because those are something you're familiar with. What's my next slide? Okay.
In the diagram at the right hand corner,
Yep.
you said 1, 2 is an E, and then you have an F outside. That does this doesn't mean that E is a subset. E is a element of F, right? You just drew that so that you want to say E is equal to F.
Yeah, these are just sets that I was drawing around. These aren't supposed to be elements. I could have drawn them as the same circle. I just wanted to separate them as an image, but I could have just done this to say they're the same set. That's another way I could have drawn that to say they're both the same set. That might be a little bit harder to see though. That's also why when I do the set things before, when I talk about sets as elements, I try to actually draw the little set symbols. So that way when I do this part, it's not as confusing. So whenever I do the circles, I mean, I try to mean that that's an actual set or a subset. Okay, there will be some practice on this. So when there are questions, those will come up for sure. Okay, so one last thing before the questions are identical sets. Okay, so this is the last thing, and you might notice there's like an equivalence here between subsets and identical sets, and then entailment and synonymy. And if you don't notice it, that's why I'm saying it, so I can point it out. Okay, so sets are identical if they have the same elements. So this is like step one. So if we say, for instance, we have a set in list notation, A, E, I, O, U, and we have a set in predicate notation, They're the same thing. So we can use them interchangeably and they refer to the same thing. Okay. If we have an active and passive sentence with the same information, exact same information specified, then they're equivalent. So the set of X such that X loves Mary, and the set of X such that Mary is loved by X, these both specify the agents of the sentence. Agents here meaning the lover. Then these are the same thing. Because if Dave loves Mary, that means that Mary is loved by Dave. If there are other people in that set, then they'll be the same people no matter whether they're the subject of the sentence or if they're the object of the preposition by there. Now, what this also means for identical sets is that if two sets are equal, then one set A is a subset of B, and B is a subset of A. So why does this happen? Okay, well, let's say that a set has two elements in it. Let's say this is set A, and then say this is set B with 1 and 2. Well, okay, if 1 and 2 is in A, then 1 and 2 is in B. So that means A is a subset of B. But that works in the other way too. If B contains 1 and 2, and A contains 1 and 2, then that means that B is also a subset of A. But these are also the same set because 1 and 2 is in one set and 1 and 2 is in the other set. Order doesn't matter, it just matters whether they're the same thing. So these are equal. So they're the same thing. And it's very similar with entailment and synonymy. If A is synonymous with B, if they mean the same thing, exactly the same thing, that means that A contains the same information as B, and B contains the same information as A. So A entails B and B entails A. So there's a nice relation here with subsets and identical sets as there are with entailment and synonymy in inferences and semantic relations. So nice little equivalence there. So that's how it is with subsets and identical sets. Okay, so let's give you some practice with subsets and elements. So most of these are subsets. I gave you one element just to make sure that you're still thinking about elements too. I'll give you 5 minutes for these ones because they take a little bit longer. Oh, that's the wrong way. But if you do have any questions, as always, bug me at any time through chat or over voice. And we'll talk about the answers in, we'll talk about the answers in 5 minutes. I muted myself before I finished the sentence. Okay, so I'm going to launch a poll for this. Basically, there's TF and DNF. So DNF just means did not finish. So pick the answers you got for the ones you did, and if you didn't finish a certain question, just pick DNF so I can see what you've got for each one. Oh, this is looking really good so far. Okay, yeah. First one. This one is true. So basically, you're taking a look at each element in the set on the left and seeing if you can find it on the right. So A can be found here, B can be found here, and C can be found on the right. So all of those can be found. So yeah, that's true. You could also draw this out um, and write everything. So S, B, A, E, G, I, C. And then you could see if you could circle A, B, and C together. And yeah, there you go. So A, B, and C can be circled inside that larger set. And there's a visual way of doing it. B, you're also correct here in that this is false. So there is no J here. If we wanted to circle J with A, B, and J, we'd have to add it outside the set. And as you can see here, J is not inside that larger set. So A, B, and J is not a subset. I thought I was J. Oh yeah, okay. There you go. That explains the one true there. So everyone got that right then. C, a little bit more contention here. So the set 0, 1 is not a proper subset of 1, 0. So this is true. This is a negative, so maybe this is why there's some confusion. So remember this, with a line through it, this is not a proper subset. So I think maybe the falses were saying that is not a proper subset. Yeah, the negation might have tricked people there. But yeah, so because these are the same size, we know that 0, 1 is not a proper subset of 1, 0 because they're the same size. For a proper subset, one of them has to be smaller than the other. And that's like the less than sign. One of them has to be smaller than the other with the less than sign. If this just were a regular subset, that would be fine. Got that wrong just because I'm sleepy now. 3 a.m. in Hong Kong. 3 a.m. You're a trooper, staying up that late. 4D, 4D, all true. Yes, that's true. B is an element of BC, as you can see right there. B is contained there. Fantastic. E, 15. The other one was did not finish. F and G, yeah, so F is found in that set, G is found in that set, and this is smaller than the other set. So F, G, H, there's the main set, and you can circle F and G. It's smaller, so this is true. F, 13 true, 1 false, 2 did not finish. A is a subset of A for any set. Yeah, so if this is A is always going to be the same set. So it's always going to be the same size as A. It's always going to contain the same elements. So yeah, this is true. It will always be a subset of itself. Every set will always be a subset of itself because it contains the same elements and it's the same size. G. Okay, this is interesting. A lot of falses here. This is also a true statement. So this is a true statement. The empty set is an empty set is a subset of every set. So there's two ways of looking at this. One is the definition. The definition says that every element in that left set has to be in that right set. Well, the empty set doesn't have anything in it. So you could say that, like, by definition, it's just true because there's nothing in that left set to check. So technically, it's true because everything is technically in that right set. Another way of thinking about it is we just have to circle nothing. As long as we can circle something with nothing in it, we're okay. So no matter what A has, as long as we can find something to circle with nothing in it, we're okay. As long as we can find some subset with nothing in it. Maybe there's a better way to explain this here. Another way of thinking about subsets is sort of in the reverse process. So maybe we can go with this. If I have a set containing 1 and 2, I can create subsets. I can basically take this set 1 and 2 and I can deconstruct it and I can say, I want to make a subset with just one of these elements. So I can create a subset with 1, or I can create a subset with 2, or I can create a subset with 1 and 2. But I can always say, what if I want to create a subset with none of those elements? I want to create a subset with nothing in it. That's always an option. So I can always choose to create a subset with none of those elements. So the empty set is always an option as a subset. So the empty set will always be a subset of any set A. So G is one of those facts that you can either sort of reason out or you can just memorize. That's both are viable options. And then H, this is also one of those true things. If you have a set A, call this A, and it's a subset of B, which means B is either the same size or a little bit larger, and B is a subset of C, which means C is the same size or a little bit larger, then A is going to be contained within C as well. Because if B is larger than C, or sorry, if B is larger than A and C is larger than B, then yeah, C is going to be larger than A. And this is why I say you can think about it the same way as the less than or equal to sign. If 1 is less than or equal to 2, and 2 is less than or equal to 3, then, 1 is going to be less than or equal to 3. I mean, these are specific numbers, but if you pick any 3 numbers where this holds, the same thing's going to work out. Okay, are there any questions about these? A lot of truths, yeah. A lot of truths. Unfortunately, when I write questions, I'm not someone who tries to balance out the truths and the falses. That's not my goal. I wish I were that type of person. That's not my intention. Don't make the exams all true. No, no. Every question I ask on anything, there's always a reason I ask the questions. I don't just randomly throw questions together or pick random answers. Okay, so we have 15 minutes left. So I think we're going to be able to get through power sets today, which will be sort of the last thing, and then we'll do set operations uh next, or sorry, this Friday. Um, we may have to push back one of the lectures, which is fine because up until the first exam, or sorry, the first test, I did leave like one class more than I thought I'd need to cover one of the lectures, which is perfect, so it'll work out. So I will adjust the syllabus and everything so that way it follows our schedule in the end. So this sort of brings us back to what I just talked about with the empty set. And here's a nice relation to natural language for possible subsets and sort of how we can deconstruct possible subsets from a big set. So when we have like quantifiers in natural language, we have words like all, some, few, many, none. These quantifiers take nouns, like groups of nouns, and they refer to different possible subsets of those nouns. So if I say something like, all of the students were very upset, or all of the people were very happy, there's a very specific set that it refers to, and that is the entire set of students or people. So we can say, like, all of the people were very happy. There's exactly one set or one possible subset, and that contains every single X in people. So basically, X here is just like every single element in the set of people. Uh, if I say some of the people or some of the students were very happy, there's a lot of different subsets this can refer to. As long as there's at least one or two elements of people in a subset, that's fine. We don't know which of those people or which of those subset it refers to until we're given a specific context, but some usually refers to one or more. It depends on the context. Like, I know some person, that's usually one or more. But if you say, I know some people, that could mean two or more, right? If you say none of the people were very happy, of course, this is like the empty set. So different quantifiers refer to different subsets. So this is what we have in natural language. Now, how do we know how many different types of, or how many different subsets there are in terms of numbers? How do we know how to construct them? Well, there's this operation we have called a power set. So before we talk about a power set, we're going to learn how to create all these different subsets. So we can just do this through a step-by-step process, like with a tree structure that I'll show you how to do. But first, I like to think about this in terms of an actual real life situation. So I like to think of this in terms of like a family portrait. So imagine we have three people in our family, Clara, Mira, and Tim, and they have a camera and they want to take a picture. They don't care about the order of where they're standing in a picture. They just care about who is in the picture. So we have this set of people. We'll call it F. This is our family. Clara, Mira, and Tim are in the set. So let's think about all the different ways that they can take a photo. So they could take a photo where nobody is in the picture. So this would be like one possible subset of people in that photo. So they could have nobody in there. So this would be like the empty set. So I just think of this as like a blank photo. Nobody is there. It's just like the background. It's not a very nice family photo, but hey, it's the scenery. That's one possible subset. They could have three different photos of them with just one person. So they could have one photo with Clara, one photo with Mira, and one photo with just Tim. So I'll just use letters C, M, and T. So we could think of these each as like a different subset. So we could think of one being the set containing just Clara, one being the set with just Mira, and one being the set with just Tim. So like each photo is like its own set. We could have photos with two people at a time. We could have a photo with Clara and Mira together, We could have a photo with Clara and Tim together, and we could have a photo with Mira and Tim together. Those could be different ways that we could put them in pairs. So each of these could be a set or a subset. So you could have the Clara Mira subset, you could have the Clara Tim subset, you could have the Mira Tim subset. And finally, you could have that nice family photo where Clara, Mira, and Tim are all together. So this would be your final subset, the set containing Clara, Mira, and Tim. And notice how this subset is really the same thing as our original set, our family, containing Clara, Mira, and Tim. So, I mean, this is just like the case where you have, okay, F is a subset of F. I mean, that's totally normal, as we saw before. Any set is a subset of itself. So, I mean, these are all the ways you can take a set of things and deconstruct all the different possible subsets. You could think of it like a family photo. Um, that's one way you could do it. Or you could learn a step-by-step tree process, which I could show you as well. But this is sort of like a visual way of reconstructing it with a real life situation. So this is how we can generate all the different possible subsets from an initial set. Now, this is only 3 people. So these are 3 things in our subsets. And how many photos did we end up with? 1, 2, 3, 4, 5, 6, 7, 8. So the more elements we have, the more different possible photos we could get, the more possible subsets we get. And it grows very fast. So when we take all these different possible subsets and we group them up into one big set, we call that the power set. And we have a special little symbol for it. So you can write it as that. It's like a little small cursive P, or you can just write a big capital P with a capital A and call that the power set of A. Either way, I like the small cursive P because it looks cool. But this is the set containing all possible subsets of A. So this is the same thing. I say let F contain Clara, Mira, and Tim. I've just abbreviated it for space as CM and T. But as you can see, the same thing from before. But now instead of having a bunch of separate little subset entries, I've now put these all into one big set. So now we have the empty set, the set containing C, the set containing M, the set containing T. We have the set containing CM, the set containing CT, the set containing MT, and the set containing CMT. And these are all contained in one big set. Okay. So first of all, what's it used for? Plural pronouns. That's your answer. So why would you use this? Plural pronouns or quantifiers. Like, what does they refer to? When you ask that question, what does they refer to? Well, in the sentence, they took a photo. They could mean any of these things, well, except for the empty set. But maybe they just means Clara, or maybe they means Clara and Mira. It would pick one of these things in this set. It would look at the power set of the family members and it would say, okay, it means one of these particular groups of people. It could mean just a singular, or it could mean a plural. Okay, so the family picture example can sometimes take a long time conceptually to work through. So there's an alternative way of generating these power sets that is more systematic and can also give you some insight into how many different elements we can get and a way of checking to see if you've actually constructed it correctly. And this will be where we finish after this example. So we can start with an empty set and we can say, okay, let's start with no elements whatsoever and let's construct a power set. So what we do is we take a look at our initial set F, or whatever set that we're looking at, that we're saying let's construct the power set for. and we go one element at a time. So we ask ourselves, uh, do we want to add C to our set? Because C is the first element here. We have C, M, and T. And we can either say yes or we can say no. Okay, if we say yes, we now have a set containing C because we've added C to our empty set. So we took our empty set, we added C, now we have a set containing C. If we don't add C to our empty set, we still have a set containing the empty set. Okay. So we've asked our first question, we've added C. What I think I have to do is I have to make these lines a little bit wider. Otherwise, I'm going to be screwed in about 1 minute. Okay. So that's the first element. We can now ask a second question. We can say, do we want to add the second thing? Do we want to add M? And we can do the same thing for each branch. We can say either, yes, we do want to add M, or no, we don't want to add M. So we have to do this for each branch. So over on the very left branch, if we have the empty set and we don't want to add M, we're left with the empty set. But if we have the empty set and we do want to add M, then we're left with the set containing M. Okay, now we have to go over to the set where we just have C and we say, okay, if we have the set containing C and we don't want to add M, we're still left with the set containing C. But if we have the set containing C and we want to add M, now we have the set containing C and M. Okay, so now we have 4 possible subsets. And now we have to finally ask ourselves the last element. Do we want to add T to it? And we repeat the same process. So for each of these options, we had 2 branches. And we can ask ourselves, okay, we have a case where we do want to add T. We have a case where we don't want to add T. And then for each of these, we repeat the same thing. So if we have the empty set and we don't want to add it, we end up with the empty set. If we have the empty set and we do want to add it, we get T. If we have the set M and we don't want to add T, we have the set M, and we continue and we continue. So the set M with T gets MT. If we have just C and we don't want to add T, we end up with C. If we have C and we want to add T, we get CT. If we have CM, we don't want to add T, we get CM. And if we have CM and we want to add T, we get CMT. Now we have 8 elements. And if we take a look at the bottom, we've gone through all of our elements. And now we have exactly the same things as we had up top. So this will look a little bit messy. But if we draw lines, it's a different order, but we have the same things. So let me get rid of those lines because it looks awful. But that's another way that you can generate power sets that is very systematic. And it tells you exactly how many members you get in order, or how many members you get in your power sets. You do not need to show this process on your assignments. This is just for understanding and also if you need to generate it yourself, if you're confused on how to do it. So if this is something that helps you generate it, then you can use it, but you don't need to show me this work. But let me show you something on the side. So it tells you how many members are in these sets. So if you don't have any elements to start with, you have 2 to the 0 or 1 element in your set, which is just the empty set. But as soon as you start looking at 1 element, you add C or not, you get 2 to the 1, which is 2 possible subsets, either the empty set or the thing with C. When you look at M then, you get 2 to the 2 things, which is 4 different possible subsets. The empty set, the set containing M, the set containing C, or the set containing C and M. Finally, when you add that last element T, you get 2 to the 3, or 8 possible subsets. So you can imagine if we had a fourth element that we wanted to add to our power set, we'd get 2 to the 4, which is 16. We had 5 things, 32. 6 things, 64. 7 things, 128. So the more elements we have in our original set, when we generate the power set, it just gets bigger and bigger and bigger. It basically doubles, or not doubles, it raises to the power of 2 every single time. So by the time you get, you know, 10 objects in your set, when you generate the power set, it has 1,024 elements. Like it gets very big very fast. So you can use this as a way of checking to see if you have the right number of things. Because let's say you have a power set with 7 elements in it when you write your assignment. You know you're missing something because it's impossible for a power set to have 7 elements. It has to be a power of 2. So the last sort of thing is like, this is sort of a fancy way of saying that if you have a power set of A, it has to be 2 to the cardinality of A. So the last question here, if E is the set containing 0 and 1, you know that the cardinality of E is 2. The size of E is 2. So what this means is that the size of the power set of E has to be the same thing as the size of 2 to the size of E, which is 2 to the 2. So that's how many elements it has to have. It has to have 4 different elements in it. So if you'd like, you can try to list out the elements of E for Friday. I mean, I'll basically start out with this and just go over it again for a refresher. But that is all I have for today. So if you have any questions, you can stick around. But that's it for power sets. Next on Friday, we'll do set operations and do some questions for that. I'll be marking the assignments today, and the solution video will be released hopefully sometime tonight, as well as your grades and the feedback. So yeah, I'll see you all Friday. Feel free to stick around if you have questions, and enjoy the rest of your week.